It's good to be back, and I'd like to take this session to explain to you my favorite geologic monument, Grand Canyon. And something as simple should be studied, and it should be able to be remembered. And the scripture in Psalm 111, verses 2 and 4. The works of the Lord are great, studied by all who have pleasure in them. He has made his wonderful works to be remembered. Made his wonderful works to be remembered. Now, I don't know about you, but I remember the Grand Canyon every time I go. It's an amazing experience. And I want to give you 5 different phrases that'll help you understand and comprehend the great geologic subject that comes to our attention at Grand Canyon. Okay, the summary of geology is in these 5 points. My mom and dad gave me the name Steve, S-T-E-V-E, and believe it or not, S-T-E-V-E will help you understand and comprehend a basic framework of geology and ultimately help us understand the whole Earth and the Grand Canyon in particular. S, my favorite subject, strata. Okay, strata. T is that word tectonics. Tectonics. The first E is erosion. Erosion. V is volcanoes. You probably figured that out somewhere in there. And the last E is exponential decline. Exponential decline. And if you can remember those 5 things in that order, and as you go to the canyon or as you look at the geology of southern Indiana or wherever you go, I think you can put this in kind of a framework. Strata, tectonics, erosion, volcanoes, and exponential decline. I'll talk about them in that order. Now, I'm going to spend most of my time talking about strata and some interesting findings from natural experiments and some field studies made in Grand Canyon. I'll talk about tectonics and erosion, a little bit about volcanoes, and then I'll get into exponential decline. Well, Grand Canyon is the world's most amazing natural wonder. I think of the 7 natural wonders, it's rated number 1. 5 million people, 6 million people or so come to Grand Canyon every year. It's internationally known. It's 277 miles long, 4 to 18 miles wide, a mile deep, 900 cubic miles in volume. It's spectacular. It has a river in the bottom, and it can be viewed from all kinds of different angles. It's an upland surface with a forest on it. It's well known for the camping experience. Northern Arizona and all of Arizona is known as the Grand Canyon State. I'd like to talk to you about strata and strata formation, and of course my favorite natural event for the study of strata is Mount St. Helens. Mount St. Helens volcano erupted in 1980 and created a whole laboratory for the study of catastrophic strata formation. And this experience and other things, other experiences I've had, like with flume experiments, has helped me understand stratification. Thursday night I explained the deposits that were up to 600 feet thick at the volcano. Every layer has a date at Mount St. Helens. We have the eyewitness observations, we have the photographs, and we can piece together the sequence of strata formation at Mount St. Helens. So that is wonderful. And I can show you right here in this cliff, the cliff exposure. The lower part of the cliff is the 9-hour eruption deposit late in the afternoon on May 18th. This is the Airfall Tephra deposit from May 18th. Then you see 25 feet of stratification here, thinly bedded strata. That's from June 12th, 1980. And then on top here you have the March 19th, 1982 mudflow deposit. A mudflow came out of the crater, spilled down out of this area, and left a rather homogeneous deposit. Now, what most interested me, and what's been of most interest to me, are these thinly bedded deposits and massively bedded deposits, especially the ones associated with what are called pyroclastic flows. Now, at Mount St. Helens, there's a 25-foot sequence of strata that was formed between about 9 p.m. and midnight on June 12, 1980. We know it was formed rapidly because we have the radar imagery of the summit of the mountain showing a gigantic plume of very dense volcanic ash in the atmosphere standing above the volcano. The ash fell to the surface, and the horseshoe-shaped crater at Mount St. Helens deflected the falling ash into a ground-hugging slurry. And this is called technically pyroclastic flow. Pyroclastic flow. It's a gas-charged slurry, rather high density of particles that are streaming along at somewhere around freeway speed, maybe twice freeway speed. And it's very hot in there, obviously, and 500 degrees Celsius perhaps. And these are, we know about them, but nobody has ever experienced or watched these at close quarters. You know why, don't you? That'd ruin your whole day. You get buried by a pyroclastic flow. Now, that's the thing that kills the geologist is pyroclastic flows because they happen so fast and they overwhelm things and very devastating nearby the volcano, especially. Well, anyway, the pyroclastic flows at Mount St. Helens are very interesting, and because of the study of those and the application, I might have some application to Grand Canyon. Let's take a look at the top part, the upper half, the upper 12 feet or so of the June 12th deposit. You can see the layering gets, the closer you get, the more vivid the layering is. What happens is there's a sweeping action of the high-density flow slurry over the surface, and it creates a tractive force, a rotational shear, if you will, and that critical tractive force at the base of the flow entrains fragments which can roll. Other fragments are held in suspension, and some other fragments bounce along, and because of the different density, the different size, the different shape of particles, these get sorted, and that's what makes the pyroclastic flows so interesting. And then the other thing is, nobody's ever been inside of a pyroclastic flow and lived to see what was going on, so we can have a lot of interesting speculation on it. Some of them are massive. Some beds are massive. Other beds are graded. Some are inversely graded, and some are laminated, and it shows the variation in the nature of the process. Some of these inversely graded beds have coarse grains at the top of the bed. These inversely graded beds are very interesting, and I'll talk about some of that a little bit more in detail. But this coarsening upward fragment or texture is an argument for a high-density flow. And then we see the thin lamination that formed, of all things, in a hurricane. Now, we are normally inclined to think in terms of stratification forming rapidly, but at Mount St. Helens, or we normally think of it occurring slowly. At Mount St. Helens, we see it forming rapidly. And this is kind of bewildering because I had thought that a catastrophe would homogenize things, mix coarse and fine and deposit them all together. Instead, in these pyroclastic flows, it segregated particles. And it segregated coarse and fine and did all kinds of interesting bedding effects, cross-bedding, ripples, and all kinds of our favorite sedimentary structures are formed next to the volcano. So it was a gas-charged slurry, and it's a fast-moving slurry, and it's about the largest fast-moving slurry that we have good experience with. Well, the application could be to rock strata like at Grand Canyon. For example, the Deposition sandstone has thin beds, cross beds, graded beds, things that are very similar to what we see the slurry-like flows at Mount St. Helens, and this may be explained that way. And most geologists are ready to appreciate how sandstones, when the sand grains are accumulating, how they form rapidly. Here's 350 feet of the Deposition sandstone in Grand Canyon. It's multiple layers. It's thought to have been deposited in the middle of the Cambrian period and perhaps 30 million years duration. Yet you look at the sand beds and you know that you can form those in a flume or at a volcano rapidly. Okay, and where is the time involved with the cliff here of Tapete sandstone? Most geologists appreciate that, from my point of view, I've got some empirical data to argue with and make a case for rapid deposition. We have boulders in the base of the Tapete sandstone. Some are up to 35 feet in diameter, which have been rolled. Okay, we have a large football-sized rock class, other things that are interesting. But anyway, it's an argument for meters per second water flow, we think. Now, water-charged slurries and gas-charged slurries are a little bit different, but they have the same principles of accumulation. A geologist in Bakersfield, California said, "Steve, you've done a wonderful job explaining how plant material may accumulate underneath floating log mats at Mount St. Helens, and how that might have an application to the understanding of coal. And that idea you have about how trees could be deposited, has application to Yellowstone. And what you're finding in the sedimentary layers in the pyroclastic flows at Mount St. Helens has direct application to Tapete sandstone. But don't you ever think about going and looking at the red wall limestone in Grand Canyon, because there's proof positive of millions of years." The petroleum geologist said that, and he kind of challenged me, irritated me a little bit. And so there it is. There's the red wall limestone in Grand Canyon. E.D. McKee and Raymond Gutshank wrote a monograph in 1969, 700-page book on that formation. And they said in that book that it was a calm and placid sea, slow and gradual sedimentation. And they suggested something like the Bahama Banks, a shallow platform, or a shelf environment for the accumulation of the beds that we see there in the red wall limestone. And I'd always known about the red wall limestone, and it's the most picturesque of all the formations in the Grand Canyon. It forms that cliff right in the middle of the Grand Canyon. And its accessibility is through side canyons and places like that, and it's cliff through most of the canyon. A geologist back about 5 years ago wrote a book review of Grand Canyon Monument Catastrophe. I think 6 or 8 page book review of my book. And he published it in the reports of the National Center for Science Education. His name is Wilf Elders. Wilf Elders said Steve Austin only found 12 nautiloids in the Grand Canyon, and he's making a big thing about this nautiloid project, but creation research is generally very bad, and especially this project going on in the red wall limestone that Steve Austin is doing. He wrote about that, and I wrote a response, and later the National Center for Science Education, Dr. Wilford Elders, geologist from UC Riverside and University of California, Riverside, and Jeannie Scott, who you might know, led a raft trip through the Grand Canyon. And the purpose of the raft trip was to refute the book that I was authored of. And of course, Jeannie Scott was defending the creation position, and Wilf Elders was the resident evolution expert. Interesting story comes as a result of that. I'll talk to you and just briefly about it. Wilf Elders called me on the phone, and he apologized for what he wrote. And he says he wants to peer review the paper that I'm publishing, or getting ready to publish. In 1998, I had some questions. Where is the uniquely creationist discovery in Grand Canyon? You know, Grand Canyon has been reinterpreted by evolutionists, or by creationists from evolutionist literature largely, but is there any uniquely creationist discovery in Grand Canyon, especially in the strata of Grand Canyon? That can be kind of a complaint, if you will, but For 9 years, I launched raft trips through the Grand Canyon, starting in 1987 through about 1995. Right in that period, every year I led a raft trip. Maybe some of you have been on those raft trips with me. Anyway, we went on these raft trips all the way through the Grand Canyon. We'd start at a place called Lee's Ferry up by Lake Powell, and we'd float down through the Grand Canyon. And we saw a lot of canyon and experienced the side canyons and had a wonderful time. If you're interested in joining us on a canyon experience, we're doing one next year in May, middle of May. The Institute for Creation Research is leading one. Okay, we often will launch in the morning, and so about 30 miles downstream is a place called Marble Canyon, and a side canyon called Nautiloid Canyon. I'll come back to that map in a minute, but the gorge is rather narrow, and there's Nautiloid Canyon, 34 miles below Lee's Ferry. It's a convenient place to camp. And for 9 years, every year, I camped 1 or 2 days at this beach right here. Here's the beach, looking directly down into the slot canyon. There's the boulders coming out of the canyon, and here's this slot canyon. And on that slot canyon there is where I found an unusual fossil called nautiloid. Some other boatmen had seen it before me, and they'd called my attention to it. But for 9 years, I started looking at that ledge. What is a nautiloid? Here's a kind of a reconstruction of what a nautiloid would look like. It's a squid in a shell, essentially, nautiloid, an extinct marine creature resembling a squid which had a solid chambered shell. And some of these are huge, like length of your arm or much bigger even. And you can see what they look like near the base of the Redwall limestone. There's this very beautifully preserved conical shell, and you see the septa forming the different chambers of the shell, and then it had the body at the wide end and had a pointy end, and so this is a fast-moving creature, probably a predator, and they occur in this limestone bed near the base of the Grand Canyon. That canyon right there is Nautiloid Canyon. Once a year I camped at that beach right there, and I studied that slot canyon. At the end of the 9 years, I had measured over 80 nautiloids on a surface. I'd eventually swept it off, I'd mapped it, done a series of studies, and I did a paper to the Geologic Society of America on why I thought that was a mass kill, that the animals, all in one layer, were somehow smothered in sediment. And I got to be expert on the geology of the Redwall limestone, and a graduate student who was doing some PhD work at a university came to me and said, "Steve, I want you to help me study a particular layer of the Redwall limestone," and it happened to be in the gorge here. So he took me down in 1989. 1988. We were down on 1988 in this area. I had 5 days camped out on that beach, and what did I do for that 5 days? The 5 days he needed was for sampling. I said, there's the bottom of the bed, there's the top of the bed, you collect that. For 5 days, I had a miniature Zodiac boat with 35 horsepower motor. I could go anywhere I wanted to in Grand Canyon. And what did I want to do? I wanted to explore the ledges all along the Colorado River here. I wanted to explore those ledges because there could be nautiloids along there, not just in the canyon, but on those ledges. I had a power boat, not an oar-powered boat, so I could maneuver in the swift current up against those ledges. And what did I find? On all the ledges, everywhere I could see it, densely packed nautiloids along 3 miles of river. And they were all over the place. And it was nautiloids galore. So now I've seen hundreds of nautiloids in that interval. They were part of the study. And so that's Marble Canyon and the nautiloids I found. Now the interesting thing, well, I'll show you some pictures here of the nautiloids, what they look like. The compass for scale. That's, maybe a 2-foot long nautiloid there. The most important thing was not that I found nautiloids, it turns out the serendipity, you know what serendipity is? You're doing something and you accidentally discover something else. Well, I knew what I was interested in was finding nautiloids. What I really found was the container the nautiloids were in, and there you see the bed at another location. Anyway, this is about 7 feet thick. It's a massive bed, and it's overlain by thin limestone and chert. Okay, and this massive bed in the middle here is where the nautiloids occur, right down the middle of the bed. And they occur on one horizon, and having looked at it in Marble Canyon, I knew enough about how to recognize it. Anyway, that's the most amazing thing, is I found the container that they were in. Now, I'll talk to you about the container because that's the most interesting thing. The sequence of strata is utterly unique, and once I got the code, essentially, or the sequence of rock types, with binoculars at a mile away, I could spot where this interval is, and so I could go anywhere in the Grand Canyon and find the interval to see if there were nautiloids there. A boatman took me to a canyon 35 miles away from Marble Canyon in the Nautiloid Canyon area. We saw where a boulder had rolled down from the cliff, a giant boulder, and in that boulder, polished by water in a slot canyon, there were 7 nautiloids around the perimeter with the same general features that you see here in the bed. The bed has coplanar nautiloids. It has large coral heads associated with the nautiloids, also has brachiopods, crinoids, bryozoans, gastropods, fusellinids. It has all kinds of interesting fossils, marine fossils in it. And it has a coarse zone in the middle of the bed, so it's inversely graded. You can see what I'm kind of indicated here. Here you see the base of the bed, it grades upward, it coarsens upward to a very coarse zone with the coarse objects being fossils, and then it fines upward above that. There are these large tube-like structures running through it. Those are fluid escape pipes, or water escape pipes that are in the bed. And so I started thinking about that, and of course it has this abrupt boundary, and it has this thin chert limestone beds that sit on top of it, and has some thicker beds underneath it. I call that Whitmore nautiloid bed. Whitmore nautiloid bed. Okay, I first saw it, let's see, here's the perspective. You see Nevada, Utah, Arizona, California. I first saw it over here in Marble Canyon in kind of north central Arizona. Then I found it in a float boulder in the central Grand Canyon, went over to the type section in Whitmore Wash, found it over there. Then I found it over in the Wallapai Reservation in western Grand Canyon. Then I found it in the South Virgin Mountains north of Lake Mead. And then I found it over on Lake Mead Boulevard in Las Vegas. Okay. And then the bed occurs without nautiloids. It thickens westward all the way across Nevada, I believe, into California. And it goes from about 7 feet thick, to about 40 or 50 feet thick as it goes westward into Nevada. And this is an interesting deposit. So I've seen all of these nautiloids, and I call a geologist for the Bureau of Land Management who happens to have done his PhD dissertation on nautiloid paleontology, and I asked him, what's going on here? I've seen thousands of nautiloids in the field, large nautiloids, and what's to be made of this? And he says, well, you and me are the world's experts on nautiloids, and you've seen more than I have. You've seen more than anybody who has ever lived on Earth, large nautiloids. Anyway, so it's interesting. The paleontology of this organism needs to be described, but they were considered to be very rare, but now we found one layer and they're very abundant. It looks like 1 nautiloid per square meter. Say the tabletop, you'd have maybe 1 or 2, probably 2 nautiloids per that area. So the desktop would be about 2 nautiloids. And so over the distance of about 180 miles, something like that, 10 billion nautiloids something like that in that layer. So that makes it very interesting. The nautiloid layer loses its nautiloids as it go northward and westward, and it's in southwestern Utah and up in northwestern corner of Arizona. And we still don't know the boundary of the bed completely, but that's kind of the where it occurs. And it's an interesting study. We've studied the location of the nautiloid bed, and we've studied the flow structures that are in the nautiloid bed, the orientation of the nautiloids and other things like that. And so I submitted to the national park a proposal. I said, you've got a whole bunch of nautiloids in the national park here, and you need some geologists to inventory your nautiloids, because look at all these organisms, okay, we have. Grand Canyon is Nautiloid National Park, okay, and the National Park Service said, yeah, this is great. We got all these nautiloids in the Grand Canyon. By the way, you should fill out this form and submit it, and we'll approve your research launch. And so they permitted us to basically break the rules in the national park by doing this inventory of nautiloids. And so we turned in January a report to the National Park Service. The National Park Service said, wonderful, you should get your study published. But you don't publish studies, so I submitted the report to another geology journal. And the geology journal, a peer-reviewed geology journal, I won't mention the name, it's the premier generalist geology journal in the world, one of the premier journals, wants to publish the paper on nautiloids in the Grand Canyon. The National Park Service said, Steve, you should take the Discovery Channel with you. And they want a documentary on their nautiloids. About 15% of the nautiloids are standing vertical in the bed. Okay, that means that the bed froze so rapidly around the nautiloids that they couldn't fall over flat. The center of buoyancy and their center of mass was offset, and these things, they crash pointing down in the bed. So in 1999, at the Geological Society of America, I presented a paper on the canyon-length mass kill of orthocone nautiloids, Redwall limestone, Mississippi and Grand Canyon, Arizona. And I had a whole bunch of geologists come, and that was a good response. I explained the mass kill and my idea of a mass kill. Now, here's what I have. I have a big problem to face. I've got all the nautiloids running through the center of the bed with big heads of coral, football-sized heads of coral that have been tipped and turned, coarse fossil debris. And I'm thinking about this problem because how do you get the nautiloids in the middle of the bed and all the coarse fragments running down the center of this 7-foot thick bed? And I thought about it for a long time. Actually, it was a 5-month process thinking about it. Started in September of 99. By February 3rd, 2000, I was ready to do the sand flow experiments. Okay, Harry Griffin Park, La Mesa, California. It's famous in the San Diego area for its gigantic sandbox. And here's my son, Joel, and I, and we're ready to do the study. You notice our equipment is not very sophisticated, but we're ready to do the sand flow experiment. Here's the giant sandbox where it all happened. And it was great. Okay, here's what we did. We filled our buckets, and then we started pouring. Okay, and when we poured, we made sand mounds, and then we started throwing sand, and then that's where it really got interesting. We produced what we could call gas-dispersed laminar flow. And this gas-dispersed laminar flow didn't allow leaf fragments to fall through it. They could not fall through a laminar flow. But as grains bounced along in a turbulent flow, they could bury leaf fragments, light leaf fragments. And as we thought about this, as I thought about it, all the good things we were learning by pouring sand, I combined two ideas. The two ideas were this: the sand flow and the pyroclastic flows at Mount St. Helens. Could we have had a high-speed underwater flow that buried the nautiloids? That was the suggestion. Combined those ideas to this. Here it comes. An idea of a high concentration, high density, fast moving, cohesionless laminar flow. And this is kind of a model that was suggested. Actually, I had read a paper by Postma written in 1988. It was in my filing cabinet. I'd written a short summary of it, and maybe that helped me combine these ideas. But anyway, I imagined this high-speed flow and laminar flow process. No nautiloid could sink through that, and large coral heads could not sink through the laminar flow. They would float like corks. And then on top of that, you would have the turbulence at the top of the flow, and that's where the nautiloids could be swept in, and then they could get buried in the tail of the flow. Do you see the kind of the model I had sketched? Okay, and I could draw the velocity profile through the flow. And this was photographed at high speed in a giant sedimentation tank by Postma and his colleagues. On a 25-degree slope, they dropped a ton of sediment from a clamshell hopper, and they photographed this. I just threw a few nautiloids in to make it kind of simulate what might have happened. So I had a model now that could explain how the nautiloids got trapped. And it's an interesting flow process. Then I went back to the volcanic literature and started modeling and thinking about how this forms. So the nautiloids are in the middle of the bed, trapped there as this high-speed flow comes by. That was the proposal. It froze very rapidly, so the nautiloids are in standing position. And it's down the whole length of Grand Canyon, all the way out to Las Vegas, Nevada. I call it the hyper-concentrated flow model. That would be probably a technical name for it. A hyper-concentrated flow is a flow about 35% sediment, 65% water. And if you can accelerate it to a high speed, it can hydroplane. And as it hydroplanes, it goes anywhere it wants on a thin film of water, essentially frictionless. And so we can explain the distribution of this bed and the rapid smothering of the nautiloids by a high-speed hydroplaning hyper-concentrated flow, a sediment-water mixture. And there you got the model, the hyper-concentrated flow model for the formation of the bed. At a speed of about 4 or 5 meters per second, a minimum speed, a high concentration flow over a level surface will hydroplane. And we know the hydroplaning parameters, and so we think that's the minimum velocity that must be involved with these flows. And it had to hydroplane because it traversed a huge area over northern Arizona into Nevada. We know the current direction from the flow orientation of the nautiloids. And so we have nautiloids over about 15,000 square kilometer area, which would be roughly 5,000 or 6,000 square miles. And then we have the non-fossil bearing bed, or the poorly fossiliferous part of the nautiloid bed, which is another 5,000 square mile area off to the north and to the west. Total volume of sediment, something like 25 cubic miles of sediment in this bed. My proposal is it came out of Colorado, swept across northern Arizona at high speed, and then moved into Nevada and probably into California. It's heading toward California where I live. That's the kind of the model I have for the layer. As it goes over a shallow platform, it goes into a slope environment. The high pressure, and as it accelerates, it's blasted apart by the dynamic pressure, and it forms a turbulent suspension. It no longer carries nautiloids or even corals in it, and it goes to a gigantic thick bed, in some places up to 50 feet thick. And then it goes into giant current structures like crossbeds and other things in the more down current direction. And so we can estimate the velocity of this flow. So here's the interpretation. Canyon length area, ocean floor collapse event, gigantic sandy debris flow or hyperconcentrated flow, 25 cubic miles or so, mass kill of nautiloids and corals and all those other creatures, flow swept dead nautiloids, burial in lime sediment. It rapidly froze around them as this flow dewatered, all this water escaping, and then the back surge deposited the thin silt beds that are overlying this bed. Now, if you look at the Redwall limestone in this bed, you'll see above it a thick sequence, 50 feet or so, of thin bedded, and that looks like that's the back surge or the tsunami that was created by this giant flow. And that could be the interpretation of the overlying beds. I've suggested that. And the last thing is limestone strata deposited in minutes. Not millions of years, minutes, okay? And that's what I want peer-reviewed in the journal, the best geology journal in the world. Okay, okay, good. The National Park Service said, we need to inform our rangers of all these nautiloids that we found. Could you please come to the south rim of Grand Canyon on August 20 and present a brown bag lunch to all of our interpreters at the National Park Service? I said, sure, I'd love to do that. They want me to bring the Discovery Channel along or some kind of video documentary to make that in the canyon, and so there's a lot of things that might happen as a result of the increased visibility of this, but it's kind of fun to see what's been happening. Let's see, anything else to be said about the nautiloid event? Well, I've talked about strata of the Grand Canyon. The lower half of the Redwall limestone looks to me like it was deposited very rapidly, okay, and it didn't take millions of years. And the same principles that we've learned in the coarse clastic material at Mount St. Helens, like in those flows, can be applied to the limestones of the Grand Canyon. The last bastion of evolutionary time, if you will, is in those limestone beds, and we may be reinterpreting those. Tectonics. Let's talk about tectonics. The first of that 5 points, the S is for strata, then we have tectonics. And here you see the assembly of continents that was published by Antonio Snyder in the year 1859. Antonio Snyder, an Italian who lived over here, I think in Ohio at the time, he published this book. He couldn't get it published in English, so he published it in French. And his book is called La Création et ses Mystères Dévoilés, The Creation and Its Mysteries Revealed. 1859, he published the theory of plate tectonics. And you see the assembly of the supercontinent before the separation on the left, and then after the separation on the right. You can see how he imagined the Atlantic Ocean basin formed. Kind of an interesting book, isn't it? Okay, we've heard about that, the idea of plate tectonics. It's become very popular. Antonio Snyder, though, was a creationist and a catastrophist. And 1859 was a bad year to publish the theory of catastrophic plate tectonics. What else happened in 1859? Darwin, right? Okay, the world didn't want to hear about catastrophic tectonics. They wanted to hear about slow and gradual process and think about geological evolution and biological evolution. So Snyder's book gathered dust on the shelf. And it was resurrected off the shelf by Alfred Wegener, the German meteorologist. About 1910, he started thinking in terms of plate tectonics, but he sketched it in a slow and gradual mode, and we call that continental drift. And continental drift theory was championed by Alfred Wegener. That theory was looked on with disdain by most geologists for another 50 years or so. Then in the middle of the 1960s, seafloor evidence suggested some type of tectonic plate separation, and so now we're thinking approvingly of plate tectonic theory. I like the theory of of Antonio Snyder, not the theory of Alfred Wegener. Continental drift, no. Continental sprint, yes. Okay, here's the plateau in northern Arizona. Notice the uplifted plateau. It looks like there was an upheaval process, perhaps at the end of the flood, sheet flooding of water off this plateau, beveling off the plateau surface, and creating this enormous erosional feature. Anyway, the tectonics that uplifted the plateau is the T in this outline. You can see the great tectonic force that buckled the Tapeats sandstone in eastern Grand Canyon. Up to 2,000 or 3,000 feet of vertical flexing of strata associated with this great upheaval event that created the plateau. 250,000 square miles of rock has been uplifted over uplifted a mile and a half above sea level. 250,000 square mile area uplifted a mile and a half. That's the Colorado Plateau. And we see the flexing process associated with these giant monoclines and faults associated with the upheaval of the plateau. And we imagine this. We also want to think about all of this huge surface. We can see the Landsat photograph of Grand Canyon with the north rim and the south rim and the canyon position through the plateau. Erosion, of course, is what we're supposed to think about. Did the Colorado River erode Grand Canyon? Well, at Mount St. Helens, we've seen rapid erosion. The most vivid example is the March 19th, 1982 mud flow. And as you see the mud flow happening, water was melted, or ice was melted inside the crater and formed a large slurry-like mud flow that came down over the pumice plain area where there was up to 600 feet of deposits blocking the valley. This mud flow largely went down to the west. It formed a hyper-concentrated flow, a very fluid-dispersed, high-concentration, fast-moving slurry, and it breached down the and ponded in places and broke a whole series of breaches through the dam. Up to 600 feet of deposits. They were breached with canyons up to 140 feet deep. Here is a solid rock canyon that was gouged out by mud. This is Lewitt Canyon, the canyon on the right, or on the left side in that previous view. Okay, it's an ancient lava flow, probably 400-year-old lava flow. Solid rock was gouged out, ancient volcanic ash bed underneath it. The whole north fork of the Toutle River Valley was blocked by landslide debris. It was unblocked on March 19, 1982 by the flow that came through there. It breached the dam, filled in a big steam explosion pit that was there, overtopped the lip of the pit and broke the dam, and then it cut back a waterfall, and it left a whole branching tree-like drainage basin. I had thought that a tree-like drainage pattern would require immense periods of time for like bifurcation of drainages, and it would maybe take tens of thousands of years for rivers to slowly eat their way into the highland areas. It was essentially unblocked in a day, and the drainage lines were established. And that kind of shows you the interesting thing about, here we are overlooking this terrain, and we see the gully-headed side canyons, the cup-shaped side canyons. You can see the plateau or flatland to the north, the flatland on the south. The breach does not go straight through it as a snaky path. It reminded me immediately of the Grand Canyon, 1/40th scale model, little Grand Canyon of the Toutle River, formed by breaching of mud. You can see the cliff there, 140 feet or so deep. This is the Wright Canyon that was opened by man-made drainage called Engineers Canyon, small stream running through a big wide canyon. Do you think that small stream eroded that canyon over an immense period of time? It might appear that way, but we have the reports and the photographs that show that canyon was open over a 25-month period. Here we see Palouse River Gorge in southeastern Washington State. This gorge was interpreted by geologists to have been eroded very slowly by the Palouse River Gorge. Many geologists went and observed this site. It's now been reinterpreted as eroded by catastrophic drainage of Ice Age Lake in Montana, the so-called Lake Missoula flood. or gouged out the channel scablands. Maybe 500 cubic miles of water was involved in the floods that gouged out the solid rock, forming Palouse River Gorge and Grand Coulee and some of the amazing features up there. The Grand Coulee is a trench 50 miles long, 2 or 3 miles wide, 900 feet deep. And that was gouged out by Ice Age floods. And so hard rock can be breached and eroded very easily. Helps us understand Grand Canyon. The Santa Cruz River in Argentina, it's a rather moderate canyon as far as canyon size goes, but it was observed by this man in the 1830s. He wrote about it in his journal. The river, though it has so little power in transporting even inconsiderable fragments, yet in the lapse of ages might produce, by its gradual erosion, an effect of which is difficult to judge the amount. He sailed up the river and saw it, and his name is Charles Darwin. He got his ideas of biological evolution from thinking about geological evolution. He got his ideas of geological evolution from reading Charles Lyell's book, Principles of Geology, and as he went up the river, Santa Cruz River, thinking the uniformitarian thoughts of Charles Lyell. Grand Canyon appears to be a giant breach structure of some type. And so catastrophic erosion and breaching. So S is strata, T is tectonics, E is erosion. And we see the erosional form of Grand Canyon. 900 cubic miles of material just eroded to make the erosional profile of Grand Canyon. We see the delta down in California in the Salton Trough. It appears abruptly, and it's the weirdest delta we can point to. It looks like a catastrophic flood of great proportion. There's evidence of a lake northeast of Grand Canyon. In the Hopi Buttes area, a lake at 6,000 feet elevation, maybe 500 cubic miles of water. Could that be involved with breaching of the dam? Could the leaky plateau, the lip of the plateau, have been ruptured some way and allowed the lake or series of lakes upstream to drain? So we're thinking about Grand Canyon in catastrophic way. Okay, and then volcanoes. Volcanoes, strata, tectonics, erosion, volcanoes. And volcanoes are very interesting. We got Hawaiian volcanoes, Mexican volcanoes. We see some of those today, but we look around the Grand Canyon, we can see volcanoes, especially in western Grand Canyon where lava is spilled into the Grand Canyon. We have volcanic ash layers in some of the beds in the Grand Canyon, although they're not very common. And to the east of Grand Canyon, we've got the petrified forest and painted desert, and that's largely a volcanic deposit. And so volcanoes figure into the Grand Canyon, especially following the strata, tectonics, erosion, and then big-time volcanoes. Volcanoes are often on the western part of Grand Canyon, and of course in the terrain to the northeast and to the east of Grand Canyon, we've got the painted desert with Petrified Forest National Park, with all those logs laying in the volcanic ash deposit. I've suggested we rename Petrified Forest National Park, let's call it Petrified Log Mat National Park. Looks like a beached log mat or something like that over there, the Shinle Formation. And here you see the upwarped area where the canyon's eroded through. Okay, let's talk about power of geologic process. From the biblical point of view, we have day 1 through 3 of Creation Week being the time when God established the foundations of the earth. By day 3, we had the continents and ocean basins formed. And so we're thinking that there was a large amount of geologic power during the first 3 days of Creation Week. And then there was a large amount of geologic power during Noah's flood on display. And then the power has dropped off exponentially. Do you see that? How it's fallen off, and then it's kind of in a low today. So we're living in a time of much diminished geologic process power compared to the past, compared to Creation Week, and compared to the flood. And that's the fifth thing I want you to be familiar with is exponential decline. So the power of process is decreased years after Noah's flood, declining power with time. And that's, I think, generally what we see. We can look at the geologic process all around us and see it in a very mild state. If you remember back to high school mathematics, they explained to you the exponential curve or exponential equation. That's a mathematical formula that describes how things decline with time, and I think it's the curve that describes the power decrease after the flood. So right after the flood, when Noah came out of the ark, the birds were going out. Everything was not hunky-dory yet. There was still a lot of process going on, but things calmed down over the years. Here you can see the declining volcano power. Mount St. Helens, May 18, 1980, 0.7 cubic kilometers of new magma came out. Mount Mazama, Crater Lake in Oregon, 75 cubic kilometers of magma came out, about 100 times Mount St. Helens size, the explosion that made Crater Lake. The Bishop Tuff near Mammoth, California, 600 cubic kilometers of tuff there. Lava Creek Tuff and Huckleberry Ridge Tuff, the last two big explosions at Yellowstone. The Huckleberry Ridge Tuff, 2,500 cubic kilometers. One of the largest volcanic explosions documented. The safe distance from which to watch such eruption would be higher orbit of space shuttle, something like that. Okay, that would be lethal over half a continent, perhaps. Scriptures to remembered. In the last days, scoffers will come, saying, all things continue just as it was from the beginning. Isn't that interesting? And we see the uniformitarian ideas about evolution, especially today. All things continue just as they were from the beginning. In other words, the establishment will disregard exponential decline with time. They are willingly ignorant of this, that by the word of God the heavens existed long ago, and the earth was formed out of water and by water, through which the world at that time was destroyed, being flooded with water. 2 Peter 3:3-6. So we are linear thinkers. We live in an age when we see constancy of rate. What are we supposed to think? We're supposed to think back of creation and the flood and the geologic power in the past, and I think we want to think about exponential decline of process. Hal Lindsey, his book, Apocalypse Code, maybe you remember Late Great Planet Earth. Earthquakes are on the increase, according to Lindsey. Earthquakes continue to increase in frequency and intensity, just as the Bible predicts for the last days before the return of Christ. History shows the number of killer quakes remained fairly constant until the 1950s, averaging between 2 to 4 per decade. In 1950, there were 9. In the 60s, there were 13. In 1970s, there were 51. And in the 1980s, there were 86. From 1990 through 1996, there have been more than 150. Increasing earthquake with time? No, he's got it wrong. He's big time wrong. We can take and plot the data. So in October 1999, I decided I would go against the establishment Christian position and say earthquakes are declining with time. And with Y2K right around the corner, I wanted to create some comfort with some of my friends. So I published this declining earthquake curve. We have very good control from seismograph data for 100 years of big earthquakes, magnitude 7 and greater earthquakes. The frequency per year appears to have declined through the 20th century. And I think that fits with my biblical point of view, that it was big earthquakes in Noah's flood, and we have declining power of tectonics with time, right? Okay, don't let Hal Lindsey sway you. It looks like the hard data suggests some type of cycle to earthquake activity. Here's magnitude 6 and above earthquakes. Okay, it looks like exponential decline is the story. So let's go over this. Okay, a summary of geology. What's the first one? S, what's that? Strata. Okay, tectonics, erosion, volcanoes, exponential decline. Okay, you got it. That's it. Strata, tectonics, erosion, volcanoes, exponential decline. Okay, keep that in your mind, and the evolutionary propaganda can be diminished. Study and remember, the works of the Lord are great. studied or sought out by all who have pleasure in them. He has made his wonderful works to be remembered. And we think about the earth, we think about Grand Canyon, we see his tremendous power and his greatness on display. Okay, thank you.